So we've been asked to find the determinants of these three matrices, okay? Can anybody remind me, if I give you a two-dimensional matrix like this, so just 4 elements, okay, what would the determinant of this matrix be? So let's call that M. What would the determinant of this matrix be? How do we calculate the determinant of the matrix? A times D, so we multiply the elements along the leading diagonal together.
B times C minus C.
Just that, isn't it? Minus B times C. Yeah? So you take these two elements, multiply them together, then you subtract that from the other diagonals multiplied together. Okay? By the way, I didn't mention this on Friday, okay? But what are the conditions for calculating the determinant of a matrix? So if I give you a matrix and I ask you to calculate the determinant of it, what does that matrix need to be? Can anybody think? Good. So they need to have the same rows as they do columns. In other words, the dimensions in each direction needs to be the same. Yeah, so when we have the same number of rows as we do columns, what type of matrix is that? Anybody remember? Begins with an S. Think about a shape which has the same... Good. A square matrix, okay? So in other words, if I give you a 2 by 2 matrix, then you're able to calculate the determinant of it. You can calculate the determinant of a 3 by 3 matrix. It's not that bad, but we tend not to look at it in this course. Even 4 by 4s we can do, okay? So as long as they're square, we can calculate the determinants of it. Fine, okay, let's come back to this then. What's the determinant of this matrix?
7 times 2.
Good.
Minus 4 times minus 6.
Good, so that times that, minus that times that, which is equal to 14 plus 24, 38, last time I checked. Good. Okay, what's the determinant of this matrix?
1 times 7.
Careful.
The opposite.
8 times 0 first.
Oh,
Okay. 8 times 0 minus 7 times 1. So that should come out as negative 7. Okay. What about the determinant of this matrix?
8 times minus 5.
Good.
Minus 4 times 0.
Perfect. So that should be equal to negative 40. All right, good. Okay. So that's just simply giving you a matrix and just doing the calculation of determinants on it. Have a go at this. So a shape is transformed using this matrix here. Negative 3, 0, 0, negative 4. Okay. First things first, I've just asked you to state the sequence of transformations which this matrix is describing. So what we're going to put here, I think there's 2 transformations, maybe 3, which we can put. How are we going to do this? How are we going to find the sequence of transformations which this matrix gives?
We are going to slowly go back.
Okay, fine. So we start off by thinking in terms of our original I and j vectors. Okay? So, sorry? No? Okay, so here we go. There's I, and there is j. So this matrix is going to be 1, 0, 0, 1. Now again, what is the name of this matrix? Anybody remember? Begins with an I. The identity matrix. Perfect. Okay. Then the idea is we just try and make this look as close to this as we can. So what's the next thing that we should do?
Put minus.
Okay, so turn them all negative. So if we make this negative and this negative, in other words, we go negative 1, 0, that's where I goes, and j goes to 0, negative 1. What transformations have we done to get to this position here? To get to this matrix here? What have we done?
You had the reflection in the both vertices.
Good, so we reflected in the y-axis because I was at 1, 0. It's now gone to negative 1, 0. So it's out here now. So that's new I, okay, new I. And j was up here at 0, 1, and it's then been flipped over to be now at 0, negative 1. All right? So that's new j. So we're getting close, like that is close to that, but we're not quite. So what else do we need to do?
We need to, like, if it's 3, we need to say that it's stretched
In which direction?
by 3
X direction, isn't it? Because that's referring to I, isn't it? Which is happening at the moment in the X direction. So it's basically being pulled by 3 in the X direction.
And reflected. Yeah.
We've already done the reflection, so they're already negative, so we've done that step now. Okay, what is that 4? How do we get that 4 there?
It's also, but it's the Y direction stretched by 4.
Perfect, it's been stretched by 4 in the Y direction, okay? So are you happy if I just list those transformations? So we have reflected in both axes. That's the first thing we do. Both axes, okay? And then the second thing which has happened is a stretch in the X direction by a scale factor of 4. Sorry, by a scale factor of 3. Happy with that? And the third thing is a stretch in the Y direction by a scale factor of 4. You happy with that? You happy with listing those? Yeah, we've done enough work with those. All good? Okay, fine. This one then follows on from what we're doing on Friday. Okay, so a square of area 3 is transformed using this matrix here, negative 3, 0, 0, negative 4. And we've been tasked to find the area of the transformed square. How could we do that? So effectively, we start off with a grid, and somewhere along this grid is a square. So let's just put him up here. Okay. I then apply my transformation matrix. Okay. Now remember, the way which you can think of this is taking every single coordinate on this grid and moving it according to this. So taking that coordinate and then multiplying this matrix by that coordinate to find where the new coordinate is. Okay, so I don't know, this shape is going to end up somewhere else after I've transformed it. Okay. Now my question is, how much bigger is this area going to be compared to the original shape?
We need to, from the first one.
Yep. Can anybody remember how we work out the scale factor between areas if I give you the transformation matrix?
Try to
Equal.
see how much each one.
So you could just try an example, you could just try any random square, multiply it by this matrix, see where the new shape ends up, and then you can work out the area from there. I agree with that, but there's a quicker way.
Yeah, we need to equal to determinants, the first one and the last one.
Absolutely, we need to find the determinant of this matrix, yeah? Because that's what the determinant tells us. It tells us how many times bigger the old shape is to the new shape, okay? So it tells us how many times the area is being enlarged, okay? So what would the determinant of negative 3, 0, 0, negative 4 be? What's the determinant of this matrix? Good. Times 0, perfect, okay? You're happy that that's an equivalent way of writing the determinant of a matrix, like absolute value signs, straight lines, yeah? Okay, so what does this come out as? 12, perfect. So that tells me that this area has been enlarged by a scale factor of 12. You happy with that? Yeah? In fact, this is what all of these determinants are also telling me. They're saying if I take some shape and I multiply by each one of these, in other words, these are my transformation matrices, then the determinants will tell me how many times bigger my new shape is, like how many times bigger the area of my new shape is. Is that okay? Yeah, so that's what determinant tells me. Don't lose sight of that, yeah? So, in other words, this original area was 3. That's what it tells me in the question. The determinant tells me that the area has been enlarged by a scale factor of 12. So what is the new area? Good. I've literally taken 3, which is my old area, and I've multiplied it by my scale factor, my determinant. And that gives me 36. Is that okay? Yeah? Looks quite big and scary and horrible, I appreciate, but it's not that bad. Okay?